For the connection between proof nets, geometry of interaction, and matrix factorizations, it's important to understand the exterior algebra as a Hilbert space. And that's the subject of this set of boards. So let me start in the very general setting. So let K be a commutative ring. Let V and W be arbitrary K modules. And suppose we have a pairing that is a function from V cross W to K, which is bilinear. There's a very general way of associating to that a pairing on the exterior powers of V and W. So for any n, there's a bilinear form defined as follows. Takes a wedge product of V's, say n of them, a wedge product of W's, say m of them, and associates to that pair the following scalar. So the sum over all permutations sigma, the sine of sigma, and then I multiply together all the pairings of the VI's with the W sigma i's. A more compact way of saying that is that's simply the determinant of the matrix obtained by pairing the VI's and WJ's in all possible ways. So that's an n by n matrix. So you can check that's a bilinear form. You can see my tensor exterior symmetric notes for that. It's proposition 29. Moreover, if the pairing between V and W is perfect, which means that the induced map from V to the K-linear dual of W is an isomorphism, then so is the pairing. I'll just say star, this one here. So in particular, V is isomorphic via this pairing to the K-linear dual of the nth exterior power of W. Alright, so what we're going to do is we're going to use this pairing defined over all n to give a Hilbert space structure on the exterior algebra of any Hilbert space. So now let's take K to be C and let H be a Hilbert space. So recall a Hilbert space, well, let's say finite dimensional, just for simplicity. So that just means that H is a finite dimensional inner product space over C, and I'll write the inner product as above. And I'm going to take the convention that the pairing is linear in the first variable, so the mathematician's convention. If you want to use the physicist's convention, you'll just have to put some bars in different places in the following. Then, by the positive definiteness of the pairing, we have a perfect bilinear pairing Okay, so what does this bar here mean? So this means take H as a C module, C vector space, where lambda, a complex number, acts by lambda bar, the conjugate of lambda. So that means that this pairing is then actually linear in both variables with that action on H bar understood. Now it's a perfect pairing because if you take H goes to H bar star, some vector goes to I guess if I wanted to be conjugate linear I should put it like that. So that map, well, it's injective by positive definiteness, and therefore for dimension reasons it must be surjective as well, so it's an isomorphism. In infinite dimensions, of course, the Rietz representation theorem tells you it's still an isomorphism, but the proof is more difficult. Okay, so we have a perfect bilinear pairing. And by what I said on the previous board, that induces a perfect pairing on any exterior power of H with the same exterior power of H bar, and taking the direct sum over all n's, we get a perfect pairing from the exterior algebra of H, well, of the exterior algebra of H with the exterior algebra of H bar. Okay, so this is just the direct sum of the pairings defined on the previous board. In particular, wedge n H paired with anything in wedge m H bar, where n is not equal to m, will be 0. They're orthogonal. Alright, so this is certainly a complex vector space. It's been equipped with a bilinear pairing. Note that the wedge H bar is bar of wedge H, so that pairing is viewed as a pairing of wedge H with itself is linear in the first variable, conjugate linear in the second, and it's positive definite by the fact that this is a perfect pairing. So that makes wedge H into a Hilbert space. Okay, so the exterior algebra of a Hilbert space is a Hilbert space, and we've checked that in finite dimension. And as I said, the ith exterior power is orthogonal to the jth if I is not equal to j. Okay, so here's a good exercise to check that if I take any two vectors, alpha and beta, that changing the order is conjugation. Now let's take H to be Cn, and I'm going to name the basis theta 1 through theta n. And I want them to be an orthonormal basis. Okay, so that determines the pairing. Recall from earlier, namely LC001.04, that the exterior algebra of H has a, well, we proved that it was a basis. The wedge products. And it's easy to see that they're orthogonal to one another and orthonormal. Alright, so what I want to now observe is that the two operators that were introduced on the exterior algebra of any module, namely wedging with and contracting with theta I and theta I star respectively, that these operations are adjoint with respect to the pairing on wedge H that we've just introduced. So the operators, again I'll just write theta I for wedging on the left with theta I, and theta I star for contraction with that dual vector. I claim they're adjoint. Okay, so we have to show that if I act on alpha and then pair with beta, it's the same as acting on beta and pairing with alpha. For any alpha beta in the exterior algebra. Now both the left and right hand side are linear in alpha and beta, so we can first of all reduce by what I just set up here to the case where alpha and beta are wedge products of theta i's. So I can assume that alpha is some wedge product, let's say of R basis vectors, and beta is also a wedge product. Now notice that just for degree reasons, if we look at the left and right hand side of this equality, they'll vacuously both be 0 unless the degrees of alpha and beta match up. That is, we need S to be equal to R plus 1 and R greater than or equal to 0. Okay. So let's just do the check. So let's compute the left hand side. If I pair theta I alpha with beta, well, that's just theta I wedged on the left with theta A1 up to theta AR. Now that's going to be 0 unless adding this index to those that already existed gives you exactly the indices that are over there. That's the way the pairing works, right? So that's 0 unless I union A1 through AR is equal to B1 through to BS. In which case it's the sign of the permutation which puts the I in the right place, so that that sequence of indices is ascending as the right hand side is. Alright, so that's what the left hand side works out to be. It's 0 unless that's true, and if it's true then it's that index of permutation. Alright, kind of run out of room here, so I'll just make a little bit of room and compute the right hand side. Well, again, that's 0 unless I is in this set of indices. And if it is in there, then we have to get the set of indices on the left-hand side when we remove I. So that's the same, of course, as saying that if you add I to the set of A's, you get the set of B's. And the sign will be the same, right? Because the sign that you get by contracting theta I star with theta B1 suppose theta I appears there somewhere. The sign that you get from that is the count of the number of things that are before theta I, but that's also the number of things you had to move, and what's left over once you remove the I is of course A1 through AR, and the sign we got computing the left-hand side was also exactly the sign of moving something past that number of elements, in that case to put the theta I in place. Okay, so we see that the sign is the same in both cases, and so we've proven that these two operators are adjoint to one another. Finally, I'd like to indicate how the exterior algebra appears in quantum mechanics. So a multi-particle state made up of d identical particles, meaning that they have identical Hilbert spaces, is specified by a sum of tensor products of one-particle states. The precise physical motivation for that I'll leave you to look up in a quantum mechanics textbook. For reasons that are also beyond the scope of this little exposition, if the particles are what are called fermions, meaning they have half-integer spin, so electrons and protons are examples of fermions. The tensor product must be alternating. So there's two ways of thinking about this, depending on whether you think about the exterior algebra and symmetric algebra as quotients of or subspaces of the tensor algebra. Usually in physics textbooks you'll see an alternating sum being introduced as just a vector in the tensor algebra where the coefficients satisfy some relations. We've introduced instead the exterior algebra as a quotient, so maybe you'll find you'll have to do a bit of translation if you look at physics textbooks. But what it amounts to is that the state is a vector in the dth exterior power of H. And if we choose an orthonormal basis, theta 1 through theta n of H, what's called the occupancy number basis of the exterior power, which is a Hilbert space, consists of what are called Fock states. So usually these are written as follows: 0 meaning there's no particle in the first copy of H, so that's unoccupied. And if the first one appears at index I1 and the second one appears at index I2 and so on, then this state is just the wedge product of the corresponding thetas. Okay, so you see here that a 0 stands for no theta 1, and a 1 stands for a theta 1. So of course there are 2 to the d in the entire exterior algebra, wedge H, there are 2 to the n possible expressions of wedge products in order. Right, that's the size of the basis. Now we know that the dimension of this is going to be n choose d. Right, you have to choose an increasing sequence of size d. Okay, so that's the occupancy number basis, and you can see here that there's a kind of binary representation of those basis vectors. Now, with respect to that basis, you'll see physics textbooks introduce the creation operator. Usually written with a dagger, and there's one for every index I between 1 and n. And the way it acts in the occupancy number basis is, well, given CI's, which are either 0 or 1, it just inserts or adds 1 to the value of CI with some sign. And some coefficient. Now that coefficient doesn't really do anything. It's because these CI's can only be either 0 or 1. And if you try and add this particle to a state that already contains it, that is, if you get a 2 here, then by the rules of the exterior algebra, that state will be 0. And the annihilation operator just removes a particle from that position. Usually just written AI. So here you can see that this coefficient here is such that if you had a 0 in this position, then you would get 0. Okay, so those are the creation and annihilation operators, and it won't have escaped your attention that we've already seen these guys before, right? So the lemma I want to conclude with says that the creation operator is just wedging with theta I, right? That's what this sign achieves here. And the annihilation operator is the contraction operator, theta I star. So these basic operators on the exterior algebra are exactly, in the case where we feed in a Hilbert space, the creation and annihilation operators that physicists are used to talking about, and the relations that we've discussed between theta I and theta I star are what are called the canonical anti-commutation relations in physics. Okay, so that concludes this set of boards and the discussion of the exterior algebra as a Hilbert space.